So we're going to go over our special cases for factoring. So first let's do perfect squares. So what exactly is a perfect square? Well, 25 is a perfect square. Why? Because we can write it as simply 5 squared. Seems pretty perfect. 4x squared is also a perfect square. So I can write that as 2x all squared. Right? For example, 2. Right? 2 is not a perfect square because what would you write that as the square of? Right? It would be 1.4 something 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 squared, which would give you 2. So that's not a perfect square. Okay. Now when we're working with trinomials, right, you can take something like this, just x plus 3 squared. Let's just call it a plus b. Okay. When we square that, we get a squared plus 2ab plus b squared. So our first and last term is pretty much a perfect squared of our first and second term in here. And then our middle term is pretty much multiplying these two terms together and doubling it. So, for example, let's look at this question. Now we want to go backwards here, so we want to factor. And we want to factor this. So, looking at this, we might notice a couple of things. One, 9 is a perfect squared. It's just 3 squared. So that's interesting. X squared by itself is a perfect squared. You can imagine a coefficient of 1 in front of it, and 1 is just simply 1 squared. Right? So that works too. Then the question is, if I were to rewrite this as just 1x, but I'm not going to write the 1, right, plus 3, and square that, does the center term work? Do we get 2ab in the center? So if I take a and b, which is 1 and 3, multiply them, and double it, do I get 6? Do I get that 2ab? And in this case you do, right? 1 times 3 is 3. You double 3, you get 6. So that actually works out. Right? So that's a perfect square. And it's exactly what we had up here as our example. Just pause there. So let's try one more together. And then I'm going to have you try one. Okay, so 16. 16 looks like a perfect square. Again, it's simply 4 squared. And here we have a 1 out in front. Okay, so do those perfect squares, the 1 and the 4, multiplied together and double it, give you 8. In this case, they do, right? 1 times 4 is 4. Double that, you get 8. So you can just write this as x plus 4 squared. Now this really is a shortcut, right? If you can notice something as a perfect squared, you can factor it like that in one step. But it takes practice to be able to see when something is a perfect squared. There's nothing wrong with actually looking at something and like this would be a simple trinomial, so you can also ask yourself what two numbers multiply to give you 16 and add to give you 8. In this case, those two numbers are the same, 4 and 4. And that's sort of your hint that this is a perfect square, right? Because if you end up with x plus 4 times x plus 4, right, we can write that as x plus 4 squared, because it's just being multiplied by itself. Right? Now this example is a little different. There's a negative here. Now we can look at this case. This is a plus b squared, but what if we had a minus b squared? How would that look like? Well, we can let me just go up here and do it. We can expand that and write it as a minus b multiplied by itself. Right? And then FOIL, so a times a gives you a squared. A times negative b gives you minus ab. Minus b times a gives you again minus AB. And then minus b times minus b is a double negative, gives you a positive b squared. So now we're left with, here are our like terms. And we have a squared minus 2ab, combining our like terms, plus b squared. So it looks very similar to this equation, except that middle term is now negative instead of positive. So if we were to look at this one and do the same thing, you might say, oh, 4, that's a perfect squared. 4 is just 2 squared. So is 2 times our perfect squared of 1 here. 2 times 1. If we double that, can we get 4? We do, but there's that negative there. So we can write this as x minus 2 squared. And you can confirm that that works, right? You can go to the side and multiply x minus 2 with itself. Right? You can FOIL it, you'll get x squared. Right? Minus 2x, and then again minus 2x, which gives you minus 4x when you combine it, and then double negative, 2 times 2 gives you 4. So that's x squared minus 4x plus 4, which is what we had here. Right? So yeah, it works. Just pause it right there. All right, next special case is our difference of squares. And that's where we had sort of a perfect squared and a perfect squared. So for example, this x squared is a perfect squared because you can, well, just put it in brackets and write squared. Subtract, and then 4 is a perfect squared because we can write that as 2 squared. Okay. Now the interesting thing is, let's take a look at this example right here. X minus 2, x plus 2. When we expand that, just FOIL it, x times x gives you x squared. X times 2 gives you 2x. Minus 2 times x gives you minus 2x. So you can see these two like terms here will cancel. It's plus 2 minus 2. And then negative 2 and positive 2 gives you negative 4. So you're just left with x squared minus 4, right? Which is what this is. So this leads to this general statement where if you have a squared minus b squared, expanding that or factoring, it's a plus b and a minus b. Right? You can go back and forth either way. So let's start with some examples like this, and we're going to factor them to look like this. Let's look at this one. Now p squared by itself, that's a perfect square. 9 is a perfect square of 3. So it looks like we can just write this as p minus 3 and p plus 3. Again, you can expand that to make sure that you factored it correctly. But let's look at the next example. You might look at this one, say, okay, well 36 is simply 6 squared, and 100 is 10 squared. So it looks like we can write it as 6m minus 10 and 6m plus 10. And you can do that. Another option, which is what I've told many of you to always do, is to first look to see if there's a common factor. In this case, there is. Let me just plot. Okay, so when we pull out a common factor, we can still see we have perfect squares here, the 9 and the 25, and so this is also a difference of squares, which we can write as 9m minus 5, 3. 3m minus 5 and 3m plus 5. Okay, now these are the same thing. So you'll notice here, let's just look at this one bracket. There's a common factor in there. It's 2, so we can pull out a 2. When we pull out a 2, we get 3m minus 5. And we can pull out a 2 for this next bracket as well. We put out a 2, and we'll have 3m plus 5. And again, when you're multiplying, the order doesn't matter, so I can move this 2 over here, and 2 times 2 is 4. We have 3m minus 5 and 3m plus 5, which is the same as doing it up here. So in this case, we pulled out the common factor first, but in this case, we didn't. Either way, you end up with the same thing. Now, in this case, you're going to want to pull out the common factor first. Why? Because you might look at 6 and you'll say, no, 6 is not a perfect square. 3 squared is 9, 2 squared is 4. Okay? 6 doesn't work. But if you pull out the common factor, because 6 actually goes into 150, you have 6 times x squared minus 25. And there's your 1, that's a perfect squared. Okay? 25 would be 5 squared. So this here is also a difference of squares. You'll have 6 times x minus 5 times x plus 5. Let me pause there.